Digital Electronics lecture series. This is lecture number 22. In the previous lecture we learned about half adder, full adder, half subtractor, full subtractor. Today we will be learning more about the adders, other types of adders. So here we can see IC 7483. So IC 7483 is a IC which is available, and it is used to add 4-bit binary numbers, two 4-bit binary numbers. As you can see, there are many number of pins, and here we have the inputs. You can see here A0, B0. So this is A0, A1, A2, A3, B0, B1, B2, B3, and here we have the outputs S0, S1, S2, S3, and C4. That is the carry. Now, how does it add? Suppose if we have two 4-bit numbers, like suppose I have to add this 1, 0, 0, 1 and 1, 1, 0, 0. Suppose these are the two numbers which have to be added. So this one is A0. Sorry, not this one. This is A0. This is A1, A2, A3, and this particular, this is B1. Sorry, B0. This is B1, B2, and B3. They are summed up, and this what we have A0, B0 added, we get S0, and if there is any carry, it goes here and adds with A1, B1, and if this is some S1, then we get here S2, S3, and if there is any carry, we get carry as C4. So these are the outputs and inputs of this particular circuit. Okay, so we will see. This is of course very easy. We have just supply the inputs and we get the outputs. This is how the IC 7483 works. Now in the coming time, now we will see this how to construct a BCD adder using IC 7483. Now before studying how to convert IC 7483 to add BCD numbers, let us see the difference between a binary and a BCD number. 4 digits binary and BCD. You have this decimal numbers. As you can see, 0, 1, 2, 3, 4, 5. I have written up to 13. Of course, I can go further. So see the difference. 0 to 9, all numbers are same. Binary 4 bits, and BCD also. But for 10 binary is 1010, while for BCD it is because in BCD we represent each decimal by 4 bits. So therefore this is 1 and this is 0, and then 11 is 1, 1. With respect to BCD, this is we can say a invalid BCD digit. We don't have any BCD number of this type, BCD digit of this type and this type. So this is what we have. We need to convert. If we have something, if the sum goes beyond 9, then we have to use a logic so that the number becomes a valid BCD. Let us see this with an example. Suppose if we are adding two numbers, like 0, 1, 0, 0 and 0, 0, 1, 1. Okay, so this is actually 4 and this is 3. We are adding these two by BCD digits. 0 plus 1 is 1, 1, 1, 1, 0, which is of course 7 as expected. Now let us check what will happen if the number goes beyond, if the sum goes beyond 9. So if we are adding, suppose 0, 1, 0, 1 and 0, 1, 0, 1. So this is actually 5 and this is 5. So now what happens? 1 plus 1, 0, carry 1. So this becomes 1, then 0, carry 1. So this number, this 1010, is an invalid BCD number. So how to convert it into valid? So the theory says that if the sum goes, whenever the sum goes beyond 9, so actually this answer would be actually 10, because 5 plus 5 is 10, and 10 actually in binary is 1010, but in BCD it should be 0001 and 0000. So this should be the answer, and we are getting this answer. Now how to convert this to valid? So the theory says that we have to add binary 6. This is binary 6. Whenever the sum goes beyond 9, then we have to add binary 6 so as to get in the valid BCD. So the 0 plus 0 is 0, 1 plus 1 is 0, carry 1, then is again 0, carry 1, then 0, then carry 1. So now this particular digit which we are having, so we can add as many zeros on the left side. So I'm just adding 3. So this is 1 and 0, which is the required answer. Okay, so we have to use this particular thing whenever the sum goes beyond 9. So we have to apply this logic for 7483 ICs, because IC 7483 it adds binary numbers. So how do we convert it in, so that it can also add BCD numbers, and we have to apply this particular logic. So let us see how we apply that logic. So now we will see the designing part, how to add that 6 whenever the sum goes beyond 9. So this is actually IC 7483. This is the truth table. You can see here, truth table means what? Here for whenever the sum, see here in this case, these are S0, S1, S3, S1, S2, S3, S0, S1, S2, S3, these are the outputs of this, and these are the inputs. So whenever this sum it goes beyond 9, we must be able to detect that sum. So we have to design that logic. So here in the first case, we see the first is from here to up to here 9. So 9 is 1001, so up to here. Okay, output should be 0 because we don't need to add anything. Okay. But as whenever the sum goes beyond 9, so from here we see 1010, then 1011, and so on up to all ones. We see we need to add a 1. Okay, because we need to add that this for this particular logic. Okay, this shows that this output has been become invalid, and we need to add 6. So this logic should be applied. So this is the truth table for applying that logic, that up to 1001, that up to 9 we are getting a valid BCD, and up beyond 9 we are getting an invalid BCD. So we must add BCD 6 to that digit. So we'll draw a K map for this. Okay, so inputs are S3, S2, S1, S0, and this is the output. So this is the K map. I've drawn the K map. Okay, this is the K map. Okay, so this is the K map. You can see we have S3 bar. So S3 bar, S2 bar, S3 bar, S2, S3, S2, and so on. These are for the inputs, and these are the outputs. Now here we can see we find a quad here. This is a quad. This is one quad, and there is another quad. These are the two quads which we obtain. So now what is the output of this is will be the logic which is to be applied. So y is first of the equation of this quad is S3, S2, and the equation of the second quad is S1, S3, S1. So this is a SOP, so we need to apply this particular logic, so that whenever there is a digit which goes beyond 1, so we need to add this, we need to add 110, 011, there is BCD 6. So this is SOP K map. Okay, so we get this particular equation. Let us see now how to draw the circuit. Okay, so here we design the logic. This is Y3 is S3, S2, or S3, S1. This is the logic we got from the K map. So of course we need here two 74i3 ICs. So 7483 IC. So this is one adder IC, this is second adder IC. The first adder is adding the two BCD digits, and this particular logic is because of this. So here we have S3, S2 going to the AND gate. This is a, you can see this one. We have this is, so this is S3, S3, and this is S2. Both are going to the first AND gate. Then we have S3, S1. So this S3 goes to this AND gate, and this S1 also goes to this particular AND gate. And then this particular logic, it ensures that whenever this sum, whenever it goes beyond 9, so this will be activated, and it will add a 6. You can see here, this 6 is why do we get a 6? Because this, what if this is 1? Okay, whenever this output, whenever it goes beyond 9, so this will be 1, and this one will be connected to the A0, A1, A2, A3 inputs, such that this is 1, this is 1, and this is 0, and this is 0. So this 0, 1, 0, 1, 1, 0 is 6. So this 6 gets connected. This gets added with the original sum, and we get that 6 addition whenever the sum goes beyond 9. Let us see with one example. So let us see. We will add one number which gives a sum which is more than 9. So suppose we are adding 0 1 0 1 and this is 0 1 0 1. Now we know this 0 1 0 1 0 1 0 will give output as 0 1 1 0 1 0. Okay, now this 1 0 1 0, because of this 1 0 1 0, we see this becomes we get, because this is S3 and S1, so S3 S1 becomes, so this becomes 1, this becomes 0, so this input of OR gate, it becomes 1. Okay, as it becomes 1, okay, what will happen, this one will make the inputs, this is already 0, this is already this is already 0, so this is 0 1 0 0, okay, 0 1 1 0 6, and this whatever sum we got, it is added with this particular, so we have this 1 0 1 0 which is added to this 6, so our sum, whatever answer we will get, so this will be 1 and this will be 0 0 0 0. So actually we can add of course 3 zeros here, so this is 1 0 whatever the sum we were expecting. So this is how a BCD adder works, and it can also be shown that if the sum is less than 9, then nothing will, this will automatically become 0. Okay, this will become 0 for that case, and 6 will not be added, and whatever sum we are getting from this adder is the sum of the adder which is below it, and that is our actual answer. Okay, so that's all for this session. Thanks for watching.